in this video we are going to talk about operational amplifiers. Now, before we get to the discussion, I would like to talk about a particular problem where we can use operational amplifiers to solve the problem rather than going for the usual method that we might be aware of or be familiar with as digital engineers, right? So let's say you want to add signals from a guitar and also someone singing. You want to mix them together and then produce some sound from one particular speaker. How would you do that? So normally in digital design, what we do is that we first convert the signals that we get from the microphone, from the person singing, and also we combine the signal from the guitar. So let's say, this is let's say this is our guitar, and then we have our microphone in here. So let's say our microphone gives this signal, and then our guitar also gives us, let's say, so it gives us this signal, and we want to add the two signals together so that we will get an output signal, and then this output signal can be fed into, let's say, a speaker, right? Now, one of the ways that we would have tackled this problem was we could use an ADC to convert this analog signal into a digital signal, and then write a script, a program that will combine the two signals in the program in digital form. And after adding them, we send it into a DAC, digital analog converter, the DAC, and then it generates the output for us, and then we feed it into the microphone, the speaker rather. So now that's a very long procedure to go by. I mean, we converted everything into digital form and then back to the analog form. We take it to make it slower, and also the quality of the signal will drop drastically. So operational amplifiers in this particular case, you can use operational amplifiers to design an operational circuit that will combine the two signals to generate the signal that we want. But before we get to that, let's first talk about what an operational amplifier is. So its circuit symbol looks something like this. So we have plus, minus over here, and then we have this, and then we have the power terminals. Normally VCC, and let's say VDD. So now we got this one V minus, and then we got this one V plus. V minus is also called the inverting input, and also the V plus is called the non-inverting input. Later on, as we go on, you understand the reason why we call them that. Now, in the circuits, we can model the op-amp to be something similar to this. So let's say we have a resistor here being connected. So let's call this Z in, and then we have this having, then we have Z out. So let's call this one Z out. Right. So what we usually, so the op-amp can be represented basically by but then it contains an internal circuitry that contains a lot of transistors, some 20 plus transistors that is used to design the op-amp. Now its behavior, the ideal behavior of what we are trying to achieve from these circuits, from an op-amp, can be summarized in, let's say, 4 ideal properties. So what we want to do, we want a device that has an open loop gain, right? An open loop gain of infinite open loop gain. So its open loop gain approaches infinity, or it is infinity. And then also from the first property, what we would want is that we want v minus v minus to be equal, or v plus to be equal to v minus for an ideal op-amp. Yes, I'll explain why that is. Now the third assumption is that the Z in, the input impedance, should be also be infinite, and then the output impedance should be 0. So the last, which is inferred from the third one, is that the current flowing through the input terminals, that is I plus, should be 0, and I minus should also be 0. So we know that no current flows through in here because the is infinite. Right. So basically we are going to, so these properties is assumed for an ideal op-amp. For non-ideal behavior, it doesn't really hold. But then for most signals, especially for signals that have frequencies less than 10, so 10 megahertz, they usually, for circuits with signals that are of this magnitude, 10 megahertz, the ideal behaviors can be, and we can approximate it for it to work practically. Or the accuracy that we get from assuming that these circuits are ideal is very, very high. So for such signals, it is sufficient. But then for signals with higher frequencies, you need to account for the non-ideal behaviors. In this video, we are only going to talk about the ideal op-amp. Maybe in future videos, we'll tackle the non-ideal op-amps and see how they also behave. So the op-amp is used in two forms. So we have the open loop properties of the op-amp, which I'm going to discuss in the brief, and also we have the closed loop properties or behavior of the op-amp. Now in the open loop op-amp, this is how we usually, it's normal op-amp like this. Now the V plus, the V minus. What we have is that we have the gain of this op-amp to be. So the gain of an op-amp or an amplifier is always V out over V in, right? So this is our gain. Now for an op-amp, the V in is always V plus minus V minus. That is the non-inverting input minus the inverting input. So what that will give us is we are going to get V out V plus minus V minus. Right. So we said that our gain is approaching infinity. So that will be studying that V minus should also approach 0 or should equal to 0 for ideal, because we can't practically get a V out equal to 0 because we have limited supply of voltage. The best we can do is making V plus minus V minus to be close to 0. Right. So yeah, so these are the assumptions that we have. Now getting this, we know for an infinite value it can be represented by constant divided by 0. Now this constant, let's say it can be 1 or any constant, but 1 is sufficient. So let's assume RA is equal to 0. So this should really be equal to 0. So, and then substituting that into an equation, you have something like 1 over 0 is equal to V out over V plus minus V minus, and then we know from here, so let's call this equation 1, or I think this should rather be our equation 1, so this is equation 2, and then we have this to be equation 3. So from equation 3, we know V plus V minus is 0, so that basically give us something like this. Now this means that we can rearrange the equation for it to be something like 0 multiplied V out. Now we know that what this equation basically means is that V out is any value, right? In the sense that we can multiply any value by 0 to get a 0. So V out can be any value. So we can force V out to be any value and then replace it there. op-amp will readjust itself to satisfy the equation for us. Alright. Now, from away from there, so what's basically like, let's say if V out is 4 volts, and 4 volts mean will satisfy this equation, and it could be any value. So we can force V out to be any value. That's what we're trying to say from there. Now this is the open loop property or the behavior, open loop behavior of an op-amp. The open loop property of an op-amp. Right? So now let's now talk about the closed loop property of an op-amp. So op-amp, you can connect them in the closed loop, and in the closed loop behavior, what we need to talk about is feedback system. We have two types of feedback. We have positive feedback and negative feedback. Now let's first talk about the positive feedback. What happens in the positive feedback is that, so we connect the positive terminal of this one to the output of the op-amp in this fashion, and then we have something like this. So we have V plus and then V minus. Now we know that from our first equation, we know that V plus minus V minus is going to give us V out, right? If we rearrange equation 2, right? I think this is supposed to be equation 2, right? So this is supposed to be equation 2, right? So from equation 2, we can rearrange equation 2 to get this particular equation. Let's call this equation 4. So from this equation, you can see that when in the positive feedback, what happens is that when you connect it at first, the amplifier amplifies the V out and the V in, so that the V out will be higher, right? Now, once V out is higher, it will cause the V positive to also go high. Now, if V positive is high, then the next one we need to further increase this, and this will further increase this, right? So in the end, the op-amp will reach it will get saturated. It will reach the maximum voltage. Now, what I mean by it reaching the saturation point is this. Now, let me draw another op-amp so that we will. So in our first diagram, I showed you that the op-amp has this terminals VCC and then VDD, right? So the VDD is usually in application we usually connect them as negative VCC. So let's say if this is 12 volts, then this will be negative 12 volts, right? Now what this means is that power can't be gotten from out of nowhere, right? So what happens is that, what I mean by saturation is the V out can rise to the point that it will get to 12 volts. Exactly. So if it gets to 12 volts, that's saturation. So positive feedback will always get the output voltage to get to saturation. Now, normally what the positive feedback is, positive feedback circuit are used for is in oscillation or oscillators. It is used to design oscillators. In this video, we are not going to talk about oscillators. We'll talk about oscillators in future videos. So I won't really talk about this a lot, but I think you might appreciate the fact that the positive feedback, the circuit is driven to the highest voltage or to saturation. So in a fraction of a second, the circuit gets to 12 volts in the positive feedback. Alright. Now away from there, let's talk about a different feedback system called negative feedback. So in a negative feedback circuit, what we rather do is that we connect the negative terminal or the inverting terminal to the output. So what happens is that instead of connecting this one, we have something like this being connected to the output. And then we have, so this is V positive and then V minus. Now from equation 4, what we can see is that, let me rewrite the equation 4 here so that you can see it. So V plus minus V minus is equal to V out. Now what happens is that in the first iteration, we know that the op-amp or the amplifier will amplify the input signal for it to rise. Now when it rises, it will cause V minus to rise. Now when V minus rises, it will cause this value, the difference, the delta V or V in, it will cause it to drop, right? Now, if it drops, it means that in the next, it will cause this to come down, cause the V out to drop. Now, if V out drops, it also drops this, causing delta V to rise. In the end, causing this to also rise. So you can see the trend. It will mean that this circuit will stabilize around a certain value, right? And that is the reason why it is used in designing actual amplifiers, because they are stable circuits, right? All right. So now let's look at a configuration that we normally use in amplifiers, and then we'll talk about the sounding circuit. In amplifiers, we can either connect it to perform an inverted amplifier or non-inverted amplifier. So first, let's talk about the non-inverting amplifier. In a non-inverting amplifier, we have something like so. So in a non-inverting amplifier, we have something like this, right? So we have something like this. So let's say we have positive and then the negative. So our signal is connected to the V positive, right? And what happened? Let me try this. So let me connect the positive and the negative. So what happens is that the signal that we are the V in that we are trying to amplify is connected to the V positive, and then this is connected to ground, right? But then that's the negative feedback, so we need to have the negative feedback loop here, and this connected in here. So we have this connected in here, then we have this. Alright, so my ground isn't really good, so let me make it better. So we have so now this is my feedback. So normally we call this one the feedback resistor, and then we call this the ground resistor. Yeah. So the resistor we are using to connect to ground. Now what happens in here is that we have our V out, right? And then we have V in, and then this is V plus, and then this is V minus. Now V minus is start from here. It's a fraction of the V out, as we can see. And our signal, the signal that we are trying to amplify, is connected in here, and then this will give us a certain output, right? Yes. So let's do the analysis to find the gain of this particular circuit. So what we can do is that we know this is V or V minus, and for an ideal op-amp, V minus is equal to V plus, right? In essence, it means that V minus should be equal to V in. All right. Now there is a voltage divider circuit. So the V minus is the voltage drop across this resistor, right? So the voltage drop across this resistor. And then since it's the voltage drop across this resistor, we can say the V minus is equal to V out multiplying Rj, so Rj over Rf plus Rj multiplying I think I've already multiplied that. So yeah, from the voltage divider rule, we can see that the V minus is equal to this. Now rearranging our equation, you can see that V out over V minus is equal to 1 plus Rf over Rg. So yes. Alright, so that's basically it. Now what we can do from here is that now we can see that our V out is also our V minus is equal to V in. So in essence, it means that our V out over V in, right, is equal to 1 plus Rf Rg. Now you can see that this is our gain, right? Now our gain is positive. That's the reason why we call it non-inverting, because if the input signal is, let's say, of this form, then the amplified form will just be a bigger form with the same similar positive to positive signal. So if the input is positive, the output will also be positive. If it is negative, it will be negative. All right. Now, and depending on, so you can see how stable this is, right? So depending on how the gain that we want, we can, let's say if you want a gain of 5, what we can do is that we can say 5 is equal to 1 plus RF RG, right? And then from here we can solve that equation to get RF over RG is equal to what? 4. So it means that RF should be 4 times RG. So it means that if you choose RF to be, let's say, if you choose RG to be equal to, let's say, 100 ohms, then it means that our RF should be equal to 400 ohms for us to get a gain of 5, right? So basically, that's how the non-inverting amplifier network looks like. Now let's talk about the inverting amplifier. It also looks similar to that, but then what we do is that we rather connect the positive terminal to ground rather, right? And then we connect this loop back transistor or resistor in this fashion. Then we have our V out, and then we connect our input here, V in, right? All right. So this is our R, and then this is our reference. So we can call this RE, maybe our input resistor, and then we can call this RF. So basically, assuming the properties of an ideal op-amp, it means that there is no current flowing through here. But the current flowing through here should be equal to the current flowing through out, because there is no current flowing through the terminals of the op-amp. Now, in that case, it also means that the voltage here, which is V plus, should be the voltage here, V minus. In that sense, it means that V minus should be equal to 0. Now, from this network, you can see that V in minus V minus over R in should be equal to V out, sorry, so rather V minus, right? V minus minus, so that we have minus right, so minus V out over RF, right? So now we know that V minus is negative, so it means that our network is going to be, sorry, V in over R in, and then this will give us V out, negative V out over RF. Now rearranging this will show us that V out V in, which is our gain, is equal to negative RF over RA. Now getting this circuit means that we can also, now you can see the gain is negative in this particular case, so it means that if our input signal is, let's say, of this form, then our output signal will be of this form, but then larger. So yes, depending on the values of RF and RE. Now if you want a gain of, let's say, 5 in this particular case, what you're going to do is that you're going to say 5 is equal to RF over RE. In that regard, you need to choose RE and RF in such a way that RF will be 5 times RE. Yes. So basically, that's also how the non-inverting amplifier works. Now let's talk about our main problem for today. So we're trying to design a circuit that can have 2 signals from a microphone and a guitar. So let's say we can connect the guitar to in a certain fashion by, let's first talk about an adding circuit. So in an adding circuit, we can have an adding circuit that's also whether it is inverting or non-inverting. But in my example, I'll use an inverting circuit, right? So in an inverting circuit, this is how it will look like. We have the same op-amp, and then our negative terminal feedback resistor will be connected in this fashion, and we have, at this point, we connect our input signals. So in this particular circuit, we have 2 signals, right? We have a signal from the guitar and then a signal from the microphone that we are trying to add. So let's say this is my microphone signal, and then this is my guitar. So we just use something simple. This is our microphone, and this is our guitar. So our guitar, sends in some signal. We're going to send here, and then this also sends in. And you can't have a loop in the signal. So let's see. So these two are sending some signals to our circuit, and then we have, let's say, so this can be R1, and let's call this R2. And what we do is that we connect this to ground, right? Now, the output of these two is going to be the addition of the two signals, right? Now, let's do the analysis and see if this is true, assuming ideal properties of the op-amp. So this will be our feedback resistor. Alright, so in here we can use superposition theory, or however you want to go about it. You can use any theory, maybe Thevenin's theorem or whatever, to do the analysis. But in my situation, I'll use superposition to find out the voltages from both parts of the circuit. So first, I'll assume there is no signal here, and then just work on this, and that will give us a V out 1, and then also work on the second part, and that will give us a V out 2. So generally, what we have is that we have always the V out N is always equal to RF, negative RF. For a negative, this is an inverting circuit. So negative RF over Rn multiplying Vn, right? Now I'll call my the voltage from the guitar V1, and then that from from the microphone V1, and then that from the guitar V2. If that's the case, it means that we are going to have V out. So there's the V out, the total V out is equal to V1 plus V2 plus dot 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 plus Vn, right? So in essence, in our circuit, what our output is going to be is we're going to get negative RF R1 times V1 plus negative RF R2 times V2. Alright, so this is what our V out is going to be. Now, if we are assuming that R1 and R2 is equal, then we are going to have V out being equal to, can factorize the RF over R. So let's call this equal to R out, and then this will give us V1 plus V2. So you can see the two signals are being added by then being amplified with this factor. But if you want the exact strength of the signal, what we can do is that we can set RF equals R, so that we have this to be negative V1 plus V2. Now you can see that the output of this particular circuit, if we select RF, R1, R2 to be equal, will be negative V1 plus V2, just like the sum of the two signals being inverted. Exactly. Yes. So our output now can be fed into a speaker, or we can invert it further. We can connect a buffer that will invert the signal again, so that we have, this will be plus here, right? So that we can have, now I decided to use the inverting amplifier because the calculation for it is quite straightforward and easier compared to the non-inverting. But basically, you can also use the inverting configuration to also perform other, or to design an addition circuit. So basically, that's how the other will work, so that we have, instead of using a microcontroller, this simple circuit can also perform the same function that we design. So yes, so that's a little bit of analog computing, right? So in my future videos, I'll talk more about the op-amp, how it is used as an oscillator, and also its non-ideal properties, and also how it is used as a comparator. So we will discuss that in future videos. Thank you.